Okay, so let's. Oh. Okay, let me start. I want to start by asking that you please be here on time. I'm talking especially to the people over there that are now sitting down. I always start 2 minutes after, but please be here sitting because it bothers me and it bothers your friends that people come in later. I'll probably have to say it once more because people will come again. So try to be here at 1:30 as much as possible. Tell your friends what I just said. Okay, so let's start. So I'm going to hopefully get later on to say a few things about administrative things, but just not to forget two things. One is I'm happy to see that many of you are already working on the problem set. You still have a week, but as I said, it's very useful to start working early so you can come to the recitation and the office hours and ask questions. Two, starting coming Thursday, every Tuesday and Thursday, maybe with one exception, there's going to be a faculty talk, an interview talk, just after this class, starting at 3, which means, one, you have the best seat in the house. If you want to stay for the talk, please do. If you don't want, try to clear this place as quickly as possible so that people can come in and be here at 3. As a result of that, I'm also going to move my office hours starting Thursday. Today is as usual at 4:30. Starting from Thursday, I'm going to move it to 5 to 6. We'll change it on the website too. Okay, so let's see where we are. Questions?
Are they machine learning talks or just?
Some will be machine learning talks and some will be other topics. But all are good talks. Lawrence. Sorry. Okay, other questions? So let's see where we are. So we talked about multiple versions of online algorithms. All turned out to be versions of stochastic gradient descent for different loss functions. And it so happened that some turn out to be mistake-driven algorithm. That is, you only update your weight vector when mistakes are being made. Others, you actually update every time. So that's one thing. We then talked about some generic improvements to algorithms. One type was regularization. Essentially, we said, really, the way people do it is they add a term to the loss function. And you can think about now these two components. And we're going to see it several more times, where the left component, the Q, really measures how well you do on the data. You minimize some loss function on the data. And the right one is a term that enforces some simplicity. We want to use simpler hypotheses. And again, we have some justification already. And we'll see more of that as we go. Maybe it's now a good time again to say it's already 1:36. I don't know what's happening today because so it's 1:36, and please try to be here at 1:30 so we can start, and it doesn't bother me and all the other people that people come in all the time. About 15 of you came after I started. Okay, so this was one form of regularization. I also mentioned another regularization via the average trick. This is one of the algorithms that you are implementing for the problem set. And actually someone asked me, I didn't say anything about it last time, but someone in the office hour asked me, why do you call this regularization? It's different. Why is this simplicity? Why is averaging the hypothesis similar to simplicity? And in fact, the argument for this being a regularization trick is a little bit different. One can show that this hypothesis is a little bit more stable under some well-defined notion of stability of hypothesis. And stability is also related in exactly the same way as regularization to the ability to generalize better, to do well on examples that you've never seen before. So this was generic improvement number 2. And the third one, we actually improved the update rule by adapting the learning rate. And again, this was a generic improvement because any loss function, you can augment it with this other grad idea. You are doing it for perceptron in your problem set. So one way to think about what we are doing here with this regularization is to think again on what this picture that we've seen before. You have this positive example, you have this negative example. You're trying to find this linear separator, which is the dark blue line here. But really, what we want to be able to accomplish is to find a thick linear separator, something that has some thickness and still fits the data. You can think about it as intuitively, it's going to generalize better if you can fit something thick, because then once the points are moving a little bit, when you see new data points, they will still stay on the right side of the dark blue line. You can also think about it, and this is the perspective we're going to take starting later today, as it's a smaller hypothesis class, right? So it's true that the class of all linear separators is infinite, right? Weight vectors, real-valued weight vectors. But if I somehow restrict myself to not deal only with hyperplane, but rather somehow with thick hyperplanes, intuitively at least, you can think about this as a more constrained hypothesis class. And we'll make this actually a little bit more explicit next week. Yeah.
So by thick you mean have more than one bias class? Can you explain it more mathematically?
Thick means that there is a margin, and you count examples as positive not only if the dot product is greater than 0, let's say. Let's assume that we transform the space. Not only when positive examples are greater than 0, but when they are greater than some gamma. And negative examples are negative not because they are less than 0, but because they are less than some gamma. So that's some kind of a thickness that you carry with you. Okay, so this is what we did. The last thing we did is we talked a little bit about the dependence of the performance of algorithms on some properties of the function space and the feature space, the instance space. And we saw some graphs like this. And you're going to play with these kind of things also in your problem set. You're not going to see exactly the same graphs because this one, think a little bit about what it means. This is counting number of errors or cumulative number of errors. And what you're going to do in your problem set is somewhat a little bit simpler to implement, basically just a learning curve. But the idea is the same. We wanted to emphasize that even though in the limit, once you have infinitely many examples, or even less than that, all these algorithms are going to learn well if the data is linearly separable or not too far from it. Different properties of the function space and the instance space are going to be responsible for how fast you do that. Okay, so questions on that? Clear? Okay, so today I want to do two things. One is develop a way to deal with nonlinear target functions. Everything we've done in the last couple of weeks has been linear functions. And this is going to be introducing kernels and what is called dual representations. And I'm hoping to start beginning of learning theory, which is going to be a section where we try to explain why learning works and understand what are the key issues that are important there. Okay, so we talked about linear functions, and linear function has some feature space. When I'm denoting here the features that I see as these xi's here, x1 up to xk. Often what we do is we don't work in this original space, but rather we map the feature space instead of a k-dimensional space here to an n-dimensional space where n could be much, much larger than k. And these chi functions here are really functions of x. In your problem set, you're already doing it when we gave you words. We ask you to look at the word before, the word after, the word two before, the word two after in the real data set. But we also ask you to consider conjunctions of these. So by this, your hypothesis class is no longer a linear function of the words, right? Because now it's becoming a linear function of conjunctions of words. It's a lot more expressive, and you can play with it experimentally. So this is really the idea that of this picture that I showed several times and will show again. I have these data points, blue and red data points. This data is not linearly separable given the x. I need a more complex function to do this. But if I take this x and just square it, I didn't change anything. I didn't add knowledge. I just changed the representation. Now I can use a linear function in the space x comma x squared. This is kind of like what you're doing with the NER problem in the problem set, and this is something that we want to do systematically today. Here's another example. I want to distinguish the green from the blue. You can agree that the function f of x is positive, being green, if and only if x squared plus y, x1 squared plus x2 squared is less than 1. Non-linear function. If I want to learn it with a linear function, I cannot in the x1, x2 space. I have to invent another space, and the space that I'm going to invent is I'm transforming the space x1, comma x2 to x1 squared, comma x2 squared. Now, in this space, this x prime space, the function is going to be evaluated to 1 if and only if x1 prime plus x2 primes is less than 1. Now it's a linear function. So in this space, all I need to do is to learn a weight vector. In this case, it's a weight vector with W1 being 1, W2 being 1, theta being 1, and I can classify using this linear function. So that's where we want to get. And to deal with this, we're going to introduce these two notions of a dual representation and kernels and the kernel trick. Okay, so let's think again about perceptron. You all understand perceptron. This is perceptron. We update if y prime, our prediction is different than the label y, we update the weight vector this way. Now, let's assume that I started with W, and I gave you these 4 examples. I'm using superscript here as the ID of the examples. X1, positive example, X2, positive example, X3, negative example, X4, negative examples. And I ran this series of examples, and you updated your perceptron. It so happened that when you did that, we made mistakes on X1, X2, and X4. What is the resulting weight vector? Yes?
W minus R times sum X1 and X2.
W.
Minus R times.
Let's assume that R is 1 for now.
Okay.
Yes.
Minus sum of X1 and X2.
It's the sum of X1, X2, and X4? Or, yes?
Would the first element of the weight vector be whatever it started at, subtracted by 1?
So I'm just thinking about the whole weight vector. I don't want to think about features now. So let's think about do vector operations, yes?
X1 plus X2 minus X4.
Why?
Because X1 and X2 are positive examples, so Y is positive and X4 is negative example.
Right, so I started with W. I added X1 because I made a mistake on it, but it was a positive example. I added X2 because I made a mistake on it, and it was a positive example. And I subtracted X4 because I made a mistake on it, but it was a negative example. Okay? You should know this, in your sleep. This is the simplest learning algorithm. We just subtract or add the weight vector, the example on which you make mistakes. Okay? So, and in general, if I want to do it, this is going to be the W. W is a sum 1 to m over all my examples. R is my learning curve. You can get rid of this R if you want. Alpha I times yi times xi, where alpha is going to be here the number of mistakes made on xi, right? Because if I made 7 mistakes on x1, I'm going to add x1 7 times. If I made 0 mistakes on x1, alpha 1 is going to be 0. I will never add x1 to the weight vector, right? So everyone agrees that this is right? So basically, I can write W as a function of the examples. All the examples, or if you want to think about it more compactly, all those examples on which I've made mistakes. Now, really, I don't care about the W. I care about the dot product relative to the W. But now I can write it this way. So f of x, which is my dot product WTX, I'm just copying this formula and dot product and computing the dot product with x. And what I'm going to get is this. This is my W here. Dot product with x. Now, these are all constants. I can take them out of these parentheses, and really what I have is that f of x is a sum, some constants, and inside here what I have is xi transpose dot product with x, which means in order to compute f at the point x, I need to write down all the xi's that I've seen earlier. And I need to compute their dot product with my current x and weigh them, sum and weigh them this way. Okay, so now I'm my example 75. X superscript I are all the examples 1 to 74. And I can compute the value, the prediction on the example number 75 by computing this over, summing over all 74 first examples. Okay? So this is called the dual representation. A dual representation means that rather than keeping a weight vector, what I'm keeping is all the previous examples. And everything I could do with a weight vector, we just proved, I can do by keeping all the previous examples. And remembering also which one I made a mistake on and which I didn't. Yes?
So M here is the number of examples you've already seen, not the total number of examples?
What I've seen so far. I don't know what will happen with examples in the future. I'm sitting now on example number 75, and I want to compute f of x for it, and I have my 74 examples that I've seen before. Yeah.
Will alpha be either 0 or 1 here?
Then no, it could be 7. So I could have made many mistakes on some examples, and I'm going to add this example many times. Right? So let's assume I would have told you that on x2 I made a mistake twice. You will add x2 and then add x2 again. Right? So the alpha 2 is going to be 2.
So the mistake being my classification of x2 or my classification of all the other x's?
On x2. So it's an online algorithm. Right? So I started with W, and then I saw x1 plus. I made a prediction, made a mistake. Saw x2, made a prediction, made a mistake. Updated. In each time, I updated the W. In this case, I added x1. In this case, I added x2. Let's assume that instead of x3 here, you saw again x2 plus, and you made a mistake. You will add x2 again. And then you saw x4 negative, you also made a mistake, you subtract x4. So it's an online algorithm, and as you go, you add stuff, and you could add the same example many times. Yeah?
How would the positive or negative be determined if the outcome was not positive or negative? It was more, if there could be more than one classification.
I'm not sure what you're asking. It's a Boolean, it's a binary classification question. So the function, as we say here, we don't say here, but we carried it with us for a long time. It's a function that maps examples to plus or minus 1, let's say. That's the problem we're solving. Yeah.
If the learning rate is 1, can we say that we won't make mistakes again and again on the same?
No, we will. So go back to the slides from last time. We talked a little bit about it and gave a way to avoid that if you really want to. But in principle, there's no reason you will not do it. It will not happen. Right? So it could be that one example is very far from the hypothesis space, from the hyperplane on the wrong side, and it will take you a long time to move your hypothesis until it's moving to the right side. Learning rate could change it. If you change the learning rate, then you can move faster. But at this point, so R is my learning rate. But in general, I could make a mistake multiple times on the same example. There's no guarantee that this will not happen. Okay, so that's the dual representation. And using dual representations, we're going to develop something that is called kernels. The general story is that this is a method that will allow us to run perceptron SVM that we'll talk about next week, and many other algorithms, without incurring the cost of keeping a very large weight vector. So you don't see it now, but there's going to be a trick that we're going to explain in the next few slides that will allow us to actually blow up the feature space, just like in the example of the green and blue points before. I moved from a linear feature space to a quadratic feature space. We can do it by adding a lot more features, and still the computation is going to be done in the original feature space, so we will not suffer computationally. An important thing that I'm going to emphasize probably several times, because the literature is a little bit confusing on this only pertains to efficiency. Everything we're going to do today is algebraic tricks. The classifier that you're going to learn with kernels is going to be identical to the classifier that you're going to get by blowing up the feature space explicitly. Using kernels isn't giving you any generalization advantage, it just gives you algebraic advantage and computational advantage in computing the prediction. And historically, kernels were known for many years. You know, it's been developed in functional analysis. You know, it's something that has been known from the beginning of the previous century. Were popularized in machine learning in the late 80s by support vector machines. I'm teaching it here using perceptron because I think it's much simpler and you can actually see what's happening. Another thing that you'll see sometimes in the literature or in papers, you'll see the word linear kernels. Linear kernels is just a nice way to say, I'm not using a kernel. I'm staying in the original linear space. Nevertheless, people bother to write it from time to time. Okay, so what do we want to do? So what I'm going to do now is I'm going to blow up the feature space. I'm going to give concrete examples, but if you want, you can keep in mind also the homework example, where you had features that are words before and after, and in addition, we ask you to generate conjunctions. W minus 2, W minus 1, W1, W2, and W minus 1, W plus 1. 3 conjunctions. Now, and this actually gives you a more expressive feature space. What I'm going to do now is I'm going to start with a feature space x1 up to xn, just like the word space that you start with, and I'm going to add all possible conjunctions over this x1 to xn as my features. So I'm going to be very, very expressive. I'm going to denote this new set of conjunctions or monomials, same thing, as the space I, capital I, and the set of monomials are going to be T1, T2, T3, and so on. And therefore, over this, now this is my feature space. My new function is this function linear sum of Wi, Ti of the example x. Now you can always write, when I wrote before Wi xi, I could also wrote Wi xi of x, because really the feature I is a function of x. Either it evaluates to 0 or it evaluates to 1, right? Think about this. A feature takes the example and decide whether the ith coordinate is 0 or 1. So I'm borrowing this notation and now I'm going to call it Ti of x. Now here it's a little bit more complicated. So let's assume that I have an example. I'm in a 5-dimensional space. These are my examples. And I'm showing you the monomial x1 and x2 and x4. What is its value on the example x? I'm claiming that it's 1. Hopefully you agree. So x1 and x2 and x4 are all 1, so it's 1. x3 and x4 of this example is 0, because x3 is 0, and x1, x2, x4 of this is 1. Right? So basically what I did, you gave me an example, and I mapped this example to a new feature space of all conjunctions. Okay? you did it in your decision tree problem. You took an example. It had 26 features in the original space, and you mapped it to a 100-dimensional space using your decision trees, decision stumps. All right, so that's what I'm doing here, only that my new features each correspond to a conjunction over the xi's. Okay, so now I'm going to run perceptron on this new function, new representation of the function. Of course, it's going to be a very, very expressive function. I can represent any Boolean function this way. Of course, I'm going to suffer because my dimensionality now is huge. Instead of n, it's actually 3 to the n. Okay, so, but still, n I'm going to have to keep a lot of weights, right? 3 to the n weights, 1 for each ti. Okay, really this is the picture that you may want to keep in mind. I started with a nonlinear function on the left. I generated new features. My new features now are things like this. x1 and x2 and not x3, x1, not x1, x4 and x3 and so on. My hope is that in the new feature space, everything is going to be simple. It's going to be a linear function. Okay, so how do we run perceptron? It's exactly the same way, right? So I just have a new long weight vector that the coordinates of the weight vector w correspond to these ti's. So each previous mistakes on example z makes an additive contribution to some of the coordinates of w, right? So I'm adding the representation of the example, the t1 up to t3 to the n, to the weight vector w. In some cases, I'm actually not changing anything. And in some cases, I'm adding 1 or minus 1. Everyone agrees? So think about perceptron. Imagine that the example is Boolean, 0, 1. That means that some of the weights are going to change, and some of the weights will not change. When will the weights change? W7. How do you know whether it's going to change when I update the weight? Say it louder. Yes? The feature 7, the T7 or X7, if it's on, then W7 is going to change. So I got an example. I made a mistake on this example. If X7 is on, W7 will change. If X7 was off, W7 will not change. In this case, instead of X, I call this T. So, and I'm saying examples are Boolean. So only coordinates of W, this is what's written here, only coordinates of W that correspond to on terms in the example Z, that is Ti of Z is 1, are being updated. Okay, so you know this. You just have to be attentive to, because this is going to be important in what we are doing. So really the value of W is determined by the number and types of mistakes, but the way it depends is exactly based on this bullet. Okay, so now I'm going to write formally what we just said. I'm adding new notation. I'm going to call by P, capital P, is the set of examples on which we promoted the weight vector. That is, we added something. D is the set of examples on which we demoted the weight vector. We subtracted the example. And M is the union of these, the set of all examples on which we made mistakes. So you already know that we only care about examples in M. If we didn't make a mistake, you could throw the example away. And now I'm rewriting what f of x is going to be. So what is f of x? F of x is just w dot product with t. which is this linear sum over all my feature. Now my feature set is this capital I, sum over all this wi ti of x. And now I'm splitting it in the following way. So I'm counting 1 of all those examples on which I promoted, where ti of z was 1, and I'm subtracting 1 on all those examples on which I demoted, and ti was 1. That's it. That's just basically what we said. So this now gives me my w. It's another way of writing w. And I want to take this w and dot product it with, so this is my wi, the ith coordinate of w. It's going to be multiplied by ti, and then we're going to sum over all the coordinates. Right? That's basically what we said. You look at the coordinate 7, and if it's on, either you add 1, if it was a positive example, or subtract 1 if it was a negative. If it was off, I don't care about 7. Okay? That's why I'm saying here, only when ti is 1 in both cases. So now I'm writing it a little bit more compactly here, this way. So I have sum over I, and inside it sum over m, all those examples on which I made mistakes, sz, tiz, tix, where sz is going to be plus or minus 1. Right? So really, what I care about is tiz. You see, I care only about tiz being 1 in both cases. And sometimes I want it as minus 1, and sometimes I want it as 1. And this is what I'm going to encode in this s of z. So I'm rewriting it here and just writing this explicitly. So it's the same thing as I had before. I'm just reminding you that s of z is 1 if z is a positive example on which I promoted, minus 1 if it was on d. So everything, all I did now is algebra. And now I can reorder this expression by changing the sum a little bit. So before I had sum of I and then sum on the example m, really I can change the order because inside it, all I have is s, which is a number, plus or minus 1. So I can write it as sum over all the examples on which I made a mistake, s of z, plus or minus 1. And inside it, oh, I have a mistake here. Okay. I wrote s of z twice, which is not good. I don't want this. Yeah. That's better. And inside I have sum of I, tiz, tix. So what is this, by the way? What is this sum here? How can you think about it? It's a dot product between x in the features t and z in the feature representative. So this is really in the t space, it's the dot product of x and z, right? And basically what I did is I just added here plus or minus 1 and summed over all the examples. So it's again kind of the dual representation that we had before. I'm going to say everything again to make sure that we get it. We have an example z. A mistake on z contributes a value plus or minus 1 to all the monomials that z satisfies. All the features, if you want, that are on. The total contribution of z to the sum is the number of monomials that satisfy both x and z. This is the dot product, right? When you have a dot product between Boolean vectors, the total contribution is the dot product, which is the sum of those that satisfy both of them. Okay, so essentially what we did, as you observed, we defined a dot product in the T space, and I'm going to call this a kernel. K of xz is the sum over all coordinates ti of z, ti of x. And using this, I can now write what I've written before. Instead of sign that I used before, I'm writing here threshold. Doesn't matter. All we care about is this. Sum over all examples on which I made mistakes. Kernel times plus or minus 1. That's it. So we got a representation which is the kernel-based representation that we had. But why do we care? I mean, why do we need to do this? Yes?
I know Z was the example you made a mistake on, but what is X the total set of examples?
So X is my current example. What I'm giving you here is the value f of X. This is my prediction. So X is the current example, and Z ranges over all that I've seen in the past. Right? So Z ranges on M. Okay? So basically what I'm saying here, in order to compute the function at point X, the current example, remember all the previous example on which you made a mistake and run this sum. Okay? Yeah.
So you may have said this, but it looks like here we dropped the like the number of mistakes that I made on the same example. Do you just add those multiple times in the sum?
Yes. Yes. So I didn't want to carry another alpha there, but because they are in the sequence, right? So in fact, I don't care about the ID of the examples. Okay. So why do I do it? Everything we've done so far is a little bit of algebra. We have this dot product that in the T space, it's going to take me a long time to compute, right? It's a 3 to the n long vector. So you can think about it as some kind of a distance between X and Z in the T space. But that's not the key thing. The key thing is that the reason I tell you this is because there is a way to compute this K of XZ in the original space, the X space, without explicitly writing the T representation of X and Z. So here is the picture, and we're going to see it 3 more times because that's kind of the key point here. I'm starting with an n-dimensional space. It's not expressive enough for me. I cannot express, I can learn linear functions, and the linear functions are not going to express the complexity of the function I care about. I'm going to blow up the feature space. I'm moving from an n-dimensional space with x1 up to xn to a 3 to the n-dimensional space. That's not necessary. Later on, you'll also move to other spaces. But in this example, 3 to the n-dimensional space. Now, if I learn a linear function on top of it, everything is going to be fine. It's expressive enough. But I'll have to compute this dot product of size 3 to the n. I don't want to do it. So the trick is that it turns out that I can actually compute this dot product in the n-dimensional space, and that's what I'm going to show you now. So this is called the kernel trick. So we look at this 3 to the n dimensional space, and my claim is as follows. Computing k of xz can be done by just touching x and z this way. It's 2 to the same xz, where same is the number of features in the original representation x and z that have the same value. Okay? So trivial. Computationally trivial. Why is that true? So I'm going to try to convince you that this makes sense. Anyone sees it and wants to give an explanation why it makes sense? Okay, so let's go over this and give an example. So essentially, this is just rewriting, but the key thing is that we want to explain why is this right. And here is why it's right. So let's take the following example. Let's take n equal 3. So I have x is 0, 0, 1. Z is going to be 0, 1, 1. There are many monomials. Monomials of size 0, which is just empty. Monomial of size 1, which is x1 or z1, x2, z2, and so on. Monomial of size 2 and of size 3. Right? The monomial of size 3, there's only one of them. Oh, there are many of them because it's including negation. It's x1 and x2 and x3, not x1, not x2, not x3, x1, not x2, x3, and so on. So these are the monomials. And basically, you'll have to write this long representation for x, which you will do in the next slide as an exercise. This long representation of z, compute the dot product. So you'll have to do it for x, 0, 0, 1. Now, for 0, 0, 1, some of the monomials are going to be on. For example, the monomial x3 is going to be on. The monomial not x2 is going to be on. The monomial x2 is not going to be on. Agree? For z, similar things. The monomial x1 is not going to be on, but the monomial not x1 and x2 is going to be on. Okay? So you'll have to write down the list of all monomials of x for z, compute the dot product, figure out how many of them align and both of them are on. And this will give you the dot product. Instead, we're going to think a little bit and think about it this way. So let's assume that same of xz is k. In this case, what is k? What is same of xz? 2, right? The first coordinate and the third coordinate are the same. The middle one isn't the same. So k is going to be 2 here. And I want to understand what monomials are going to survive in this dot product that I'm going to do, right? So my argument is this. I'm going to take this first coordinate and third coordinate and generate all the monomials that they participate in. Okay? What is the biggest monomial that that survives both of them? Not x1 and x3 survives both of them. Agreed? Not x1 and x3. If you add x2 somewhere there, it will not survive because in x it's going to be, so either it's positive or it's negative, the x2 that you add there, and either z or x is going to kill it. So, but not x1 and x3 is going to be the longest surviving monomial. Agreed? Now, what about all the subset of this? So you see here not x1 and x3, and you can take subset of it, just not x1, or just x3, or nothing. They will also survive. So you have the longest surviving monomial, all its subset, all these are going to survive. Anything else that you want to add will not survive because either x or z is going to kill it. So how many are there if I take k, a monomial of size k, and all its subset? This is where the 2 to the k comes from. I have a monomial of size k, and for each component, I can decide, do I keep it there or do I drop it? So I have two options, size k, 2 to the k. Okay? Let's look at this example here that does in a concrete way what I just said. Font is a little bit small, but I just gave you exactly, so this is what's written here. This is x here, and this is z. And I'm writing the monomial, the longest monomial that survives. It's the red one is negated, so it's, you can see it well here, you'll see it well on the slide. So it's not x1 and x3 of 0, 0, 1 is equal to not x1 and x3 of 0, 1, 1. They're both 1. And then all their subsets are also going to be on, and that's it. Nothing else is going to be on. Yes? Oh, okay, so for now, I'll go back to it in a second. For now, let's just assume I have two vectors, x and z, and all I want to convince you is that computing this dot product is equivalent to do 2 to the same xz. Convinced with that? Everyone is convinced? So now back to your example. The way we're using it, x is my current example. I'm computing f of x, right? So I now care about predicting for x, and z, I'm summing over z. These are all the examples that I've seen before. So I'm going to compute k of xz, fixing x, ranging over z, all the z's that I've seen before. Okay? That answers your question?
Are the zeros and ones meant to labels?
No. So these are just the bits of x. These are the features of x. These are the features of z. Okay, so x is a Boolean vector. Feature 1 is 0, feature 2 is 0, feature 3 is 1. Same for z. So these are three-dimensional examples. In your homework example of, let's say, the NER, you had 7. Well, you have a lot more dimensions. Most of them are 0, but some of them are 1s. So this corresponds to these features. Questions? Okay? Yes?
Does Z range over all the examples seen before, or all the examples that were mistakes?
The way I've written it here is only those that I've made mistakes on. Because in the way I've written it before, you could sum over all the examples, but then you have to have a coefficient of how many times you've made a mistake on something, and some of them will zero out. An example that you did not make a mistake on does not contribute to W, right? So I can just throw it away. So I kind of make it more compact by just summing over M, which is the set of examples on which I've made mistakes. And this gives you another sort of perspective that will be useful here and will be useful later on in other algorithms. Really what's important, not all the examples are important. Some examples do not contribute anything. For example, if you have examples that are far to the plus side and far to the minus side, they will not contribute anything. You don't learn from them. You really learn from those examples that are kind of in the middle, close to the hyperplane, because during learning, you might have made mistakes on them, and they taught you something. Those that are farther away didn't teach you anything. Okay, so what have we shown? Okay, so this is, you will have to go over this example again. I mean, I'm sure that it's subtle. And I suggest that you'll also go over this example. So I'm kind of giving you a recipe here for an example that I want you to look at. Take an example, 4-dimensional example. Look at the space of all monomials. For the case of 4, this is 81-dimensional space. Don't write 81 dimensions. It's too much. Write only the own variables. For the two examples that I've given you, I gave you x is 1100 and z is 1101. Write their t representations. Compute the dot product. You will get 8. How do I know that you'll get 8? Because the same of x and z that I gave you is 3, and 2 to the 3 is 8. So just as a sanity check, do this exercise and see what happens. So, okay, so what have we done? We've developed a dual perceptron. Simply run perceptron in an online mode, keep track of the set M. That's your question. Keep track of all the examples on which you made mistakes. This example, this set M is dynamic, right? As you move, it changes because you add examples to it. Also keep track of S of Z, whether the mistake was positive, whether it was on a positive example or a negative example. Rather than remembering the weight vector W all the time, you remember the set M and S. And now you can compute this function at the top there. For every point x I gave you, you can compute it by remembering M and computing k of x z, where z ranges over all this M. Okay, so we did a kernel. I'm going to move and do a few other kernels. Eventually, we'll get the idea. Here's another kernel. The example that I gave you here was also a polynomial kernel in the Boolean space, but we can generalize it and have a polynomial kernel in the general space. Here is the first polynomial kernel that we're going to do. So, given two examples, x and y, n-dimensional, what I want is I want to map them to a higher dimensional space, because the target function isn't expressive enough over this. Again, think about this ellipsoid that I showed you, green and blue examples. So this is my mapping. I'm going to take this x1 to xn and map it to something that is quadratic. I have a zero-dimensional term, 1. I have the x1 up to xn. I have all the squares, and I have all the mixed squares. Order of n square dimensions. Same thing for y. Now, my learning algorithm is a learning algorithm that needs to compute dot product, right? We showed that. We've written the dual representation, first slide on this, and we showed that we need to compute xi dot product with x, or z dot product with x. So I need to be able to compute phi of x times phi of y in this case. One way to do it is to just write this down and compute it, so it's going to be order n square computation. My argument is that, no, the kernel trick says that you can actually remain in the n-dimensional space and do it. Here is how. Take the n-dimensional representation of x, dot product it with y, add 1, square the number that you get. Okay? This is going to give you a number, add 1 square, it's the same thing. This is a theorem, right? What I said, the theorem is A equal B. Proof, do the algebra. Just open the parentheses and compute it. Really, I'm cheating you a little bit because I should have written square root of 2 on the mixed coefficients. I didn't want to do it. But when you do the algebra, you'll see that you need the square root of 2 there. It doesn't matter really if you use it or not, because the linear function will figure out which coefficients it likes to put there anyhow. So you can start with 1. But that's the kernel trick. Again, I want to work in the n square dimensional space, quadratic, but I want to do it without working in the n square dimensional space. So I'm using this trick. So trying to articulate the trick again, you want to work with degree n polynomial features, phi of x. Then your dot product will be in the space of dimensionality n choose 2, n square. The kernel trick allows you to save and compute the dot product in an n-dimensional space. Now, the same thing is going to work if you want it in a 7-dimensional space. So it's going to be n to the 7 rather n square. Now, of course, you could ask the question, can I use any n, any k, any kernel? It turns out that you cannot. Not everything can be plugged in. Not every operator that takes x and t and does something to them can be a valid kernel. A function k of xz is a valid kernel if it corresponds to an inner product, to a dot product in some feature space. Let's take another example. So I'm going to give you another quadratic kernel. This time without the 1. Before I had dot product plus 1 all square. Now I'm not including the 1. It's going to be easier to write. It's another kernel. It's also quadratic, but it's another kernel. So, and I'm going to prove you that this is a kernel by showing you that you can write it as a dot product. in the new space. So this is the kernel, K of xz. I'm using 2 dimensions, okay? So x is x1, x2, z is z1, z2. And what I've written here is the dot product of x and z, okay? Square. Now let's open the parentheses. That's what you're going to get. You're going to get these mixed squares, mixed term, and mixed squares, okay? A plus b all square, you remember? And what I'm doing here is I'm decomposing it to a product. If you think a little bit about it, you should go the other direction to check. What you really, this sum can be written as the dot product of x1 square, square root of 2 x1, x2, x2 square, that's vector 1, dimensionality 3, times this vector, dimensionality 3, transpose. So just to confuse the enemies, because I'm using, typically we have vectors, we think about vectors as column vectors. So I write W transpose X. Here, because I don't know how to write column vectors, I'm writing row vectors, so I'm putting the transpose here. But hopefully you don't care. So basically what I showed is that I can take this K and write it as a dot product of 2 3-dimensional space vectors. I call one phi of x and the other one phi of z, or phi of y it should have been. So what I did is explicitly I proved to you that it can be written as a dot product, therefore it's a kernel. This is exactly the example from that green-blue thing, okay? Where I started with a nonlinear function, I blew it up to the quadratics, and I got a linear function. Okay, so now, really, there is no need to explicitly show the feature space phi, as I did here when I showed you, oh, okay, there is a 3-dimensional space such that the dot product in it is equal to your kernel. Really, there is a more general condition that involves writing all the dot product between all the x's and the z's that you have in your data. It's called the Graham matrix, and if it satisfies some property, then it's a kernel, even if you don't know how to write it explicitly as a dot product. I'm not going to care about it. What I'm going to do in the next few minutes is give you a few more examples of kernels. We've seen all 3. This is a linear kernel. Basically means stay in the original space, just compute dot products. This is the kernel that we just talked about. We talked about the case d equal 2, but you can do d equal any number that you want. Polynomial kernel. This is where I'm adding a constant. So I showed you xz plus 1 to the power 2. You can do to the power d, and you can do c here. Basically, because I added this constant here, you'll get all monomials of all degrees up to degree d. Here you'll just get degree d. So these are examples of polynomial kernels, very useful kernels. When you play with SVM in your homework, don't use kernels, but you can see that there is an option to use kernels. Okay, there are many, so I'm not going to go over this in details. I just want to kind of give you the idea that you can construct new kernels. If you have a kernel, you can build another kernel. For example, if K is a kernel, C times K, where C is a constant, is also a kernel. If K is a kernel and F is just a function that you can apply to X, then F times K times F, Fx, Kx, X prime, Fx prime is also a kernel. And many other kind of very simple functions, sums, products, and so on, of kernels are also kernels. In all these cases, it's actually very easy to show that this is a kernel. Let me give the example from here. So if I told you that K is a kernel, What does it mean there is a kernel? That there is a dot product in some space, let's call the space phi, and k of x comma x prime is equal to a dot product phi of x and phi of x prime. If I told you that, you should be able to convince me that c times k is also a kernel because you'll show me the dot product. In this specific case, you'll take square root of c and put it in the phi, and therefore the new dot product is going to give you c times. And you can do the same kind of trick directly from the definition for any kernels. Okay. The final important kernel that I want to talk about is this Gaussian kernel. This is a continuous kernel. Everything we did before, there were discrete kernels. This kernel is defined this way. You take two vectors, x and z. It's e to the minus x minus z to power 2 over c. So let's forget c for a second. Think about it as to the power 2. So what will you get? You will get that if x and z are very close, k of xz is going to be always 1. Right? Because you're going to get e to the 0 there. If x and z, and when x and z are different, you can go down to 0 as a function of how different they are. So you're going to get something like this, the picture that I show here. Now, c is going to influence this a little bit. If c is very small, you're going to get basically a flat thing. If c is going to be very large, the other way around. If c is very large, everything is going to be the same. But it's easier to think about c as a small constant. And there, what you will get is something like this. Basically, when x, it basically tells you, it measures the similarity between x and z and transforms the space this way. When x and z are similar, it's peaked. When they are far apart, it goes down. And this is, again, a very useful kernel. I'm not going to go over it now, but you can take this, go over this slide, and what I'm doing here is I'm proving that this is a kernel, and the way I'm proving it is I'm starting with a linear kernel. You know it, a dot product is a kernel. And I'm using all the operators that I had 2 slides ago to construct a Gaussian kernel, and this way you should be convinced that this is a kernel. Okay, summary. What do we know? So kernel-based methods provide a collection of methods to run perceptron or SVM or other functions, other classifiers on a very large feature set without incurring the cost of keeping very large weight vectors, very large example. So because we figured out this trick that allows us to compute the weight vector in the original feature space. Warning, this is really only efficiency. It has nothing to do with the classifier being better because you run the computation more compactly. It's really the same classifier. Hopefully the algebra that we've done earlier today convince you that you can either compute the dot product in the T space or figure out the trick and compute it in the X space. But the result is the same result. And therefore, generalization properties of this classifier have nothing to do with the kernel trick. It's relative to the real dimensionality, the blown up dimensionality that we have. And there are many, many algorithms that enjoy this trick. SVM, Gaussian models, PCAs, all have kernelized versions. Okay, so an important question here is, do I always want to use a kernel? Yes or no? And there are 2 issues here. One issue is complexity. Is it really going to save me something? and the second issue is generalization. So for the computational aspect, I'm doing here some simple back of the envelope computation just to give you an idea. So we can either work in the dual space, which is what we talked about now, or we can work in the original space, which is also called the primal space. If we work in the dual space, we use kernels. If we work in the primal space, we blow up the feature space, any dimensionality that we want. In the dual space, operations are going to be something like m squared, where m is the number of examples, time the dimensionality. Let's say T1 is the dimensionality when we work in the dual space. Because that's going to be the cost that we have. Remember, you sit on an example, you have to compute its dot product with everything in the past. So that's m operations. And you have to do it for each example, so this is where the m squared kind of comes in. Okay? For each example, you have to touch all the other examples, so it's quadratic. In the primal space, you don't. You just do something that is a function of m times T2, which is my dimensionality here. Computing the dot product requires touching all the dimensions. Now, this is sufficient to think about it in the following way. If T1 is much, much smaller than T2, it boils down to the number of examples, the m. And what you can see here is that if you have a lot of examples, m is going to dominate. Use the primal space. Don't go to the dual space, because there you're quadratic in m. If you don't have a lot of examples, okay to use the dual space. So that's kind of a hand-wavy argument, pretty correct. So that's one issue. The second one is generalization, right? So I'm asking the question, do I really want to use kernels, yes or no? So we gave one argument here from the computational perspective. In the extremes, huge number of examples don't, small number of examples do. Generalization. Do I want to use the most expressive kernel I can? That's something that you can actually answer because you already thought about it. So what does it mean to use the most expressive kernel? Okay? Is to use the largest feature space possible, right? The most expressive function you can. Do you want to do it? It might overfit. And that's kind of a basic principle that we carried with us for a few weeks now. So if I start with x1 to xn, and I'm going to add all the monomials, or if you want, even all the monomials of size 2. So you have your example for any R now, and you're looking at a small window around the target word and conjunctions. You could imagine, you know what, I'm going to actually look at all the sentence as my W's, W minus 7, minus 6, minus up to the end of the sentence. And I'm going to look at all possible conjunction of size 2 of this. So I'm going to conjoin W minus 7 also with W1, with W2, with W6. You could do this. What I suggested is just take very few conjunctions, not all possible conjunctions of size 2. And the reason is that I think that some of them are irrelevant, and one can show that if you just add features and they are irrelevant, you're going to suffer. So I'm not going to show you the argument. It's in the slides. I hid this slide, but it's basically there. So the basic idea is that you have to think a little bit before you use kernels irresponsibly. Okay, to conclude, the use of kernels to learn in the dual space is an important idea. And there's a lot of work on use of kernels, on restricting the use of kernels different ways. Basically, what we are doing is we are embedding the original space in a larger space and Sometimes this can affect generalization, so we have to be careful with what we do. Now, the theory of kernels is much, much broader than what I kind of gave you in one lecture. I talked about polynomial kernel and Gaussian kernels. In fact, for every structure, you can invent a kernel. So if you're interested in parsing, which are trees, you can invent kernels over trees. And essentially, think about subtrees as your features instead of just nodes in the tree. And you'll have to do the algebra and figure out how to develop a kernel over these trees, but this will give you a good intuition for what kind of features I care about when I deal with structure. If you work over graphs, you can take subgraphs as your features and develop a kernel that corresponds where the features correspond to subgraphs in this. Just like when we developed our features, the TIs were monomials over the XIs, you can make them subgraphs. So again, I'm not going to give the details. In all cases, the picture that you want to have is something like this. Questions? Yes? Up there.
When you talk about the most expressive kernel, are you talking about all the quadratic kernels, or we're talking about kernels to a higher power?
So this applies in both cases. It applies, let's assume you start with x1 to xn. Let's assume that you only want to do quadratic kernels. You have two options. We have more, but let's talk about two. You can take all the quadratic terms over x1 to xn, or let's say that you know that your x1 to xn correspond to words in a sentence. You will decide not to take all the quadratic terms, but only quadratic terms of consecutive features. So you will never have x1 and xn, or x1 and xn minus 1. You just have x1, x2, x2, x3, x3, x4, and so on. So limited quadratic. So this is a decision that you'll have to make. In a similar way, you can decide whether you want to go quadratic, or degree 3, or degree 4, based on what you expect will be relevant in your domain. And even then, maybe you want to filter and not take kind of long-term dependencies into account if they correspond to something physical, like a sentence or like an image, where you think that things that are very far apart do not matter. Yes?
Once you found sort of a way of blowing up the feature space that makes the examples linearly separable, is there any need to try other blown up feature spaces, or is the only goal really to get linearly separable feature space?
So the only goal is to get reasonably good performance on your training data. You'll decide what's reasonably good. Because if you don't get it, there's no chance that you will learn. And you often need to blow up the feature space enough to get there. No need to go beyond that. Yeah. So they are not considered kernels. In this case, you explicitly blow up the feature space. There is no theory of how to think about this as a kernel. You really have to touch all the decision stumps. So this is an explicit blow-up of the space. Okay, so we didn't get to theory today. I just want to remind you that problem set is due next Monday. And the exam, the midterm exam, is next Thursday. Please use the recitations and the office hours for both of these.
I'm just wondering, what's the term going to look like? Is it more like quiz, or is it like short answers?
We'll give you a few examples.
Okay. And also, how many layouts we can use for this?
Oh, I should have said it. One.
Oh, just one?
Just one. We said it on Piazza, we'll say it again. Yeah, because we don't want you to carry it all the way to the exam.
Oh, yeah. Oh, it's on, the exam's on Tuesday.
On Thursday.
On Thursday. It
Yeah.
is due on Monday.
It's due on Monday.
Well, why can't I just only use one day? Is that
Because two reasons. One, we want to give you solutions. Two, we want to force you to stop at some point and prepare to the exam.
right? That makes sense.
So,
Thank you.
hi.
I'm Priya, by the way.
Hi.
Hi. Right now I'm in Sys 519, and I was wondering if I could switch to 419. I sent you an email.
Yeah, yeah. So, just a second.
I'm not 100% sure if I want to switch yet. I know 519 requires a project.
Yes.
I'm a sophomore right now, and this is my first machine learning class, first Python class actually.
Oh, I
So I
see.
don't know if I'll be able to keep up with the project.
Do you have a team to work with?
I have a couple people I could work with if I wanted to stay in 519. But I'm worried I won't be able to contribute much to the group if I do.
It's really up to you. It's going to be a lot of work for sure, because the idea is that it's part of your grade. So I don't know. It's hard for me to judge because I don't know where you are in terms of how much time you have and how much load there is. When do you have to decide?
I think soonish. I need to talk to my advisor.
I can sign and then you decide whether to turn it in or
Okay.
not.
Yeah.
So,
Thanks. So for 419 students who don't have to do the project, is the grading be different than would exams be weighted more?
no, it will be, so what will happen? Well, okay, indirectly, yes, because there's going to be a grade, and for the 519, we're going to scale it with the project that will be about a quarter of the grade. But other than that, it's the same. So,
Okay, thank you so much.
sure.
Quick questions. To the average perceptron, do you know how long it's supposed to take to run on that news data? Because it's
You use the sparse representation that you suggested?
Yep. And it works fine on the synthetic data. It takes but it takes forever on
No, it shouldn't take forever. Even one iteration?
yeah, it takes like 15 minutes.
No, something like that.
Any recommendations on are there good ways to update your dictionary values or is that just standard?
What I suggest you do, start with the example that we gave. We gave you feature extraction, only 2 features. I think for that, it runs in seconds. You will not get really good results, but you will get okay results. And this will give you more confidence that what you're doing is okay. So basically start with the feature extractor that we gave. Any of you ran with the feature extractor that we gave? Just the 2 dimensions? Yeah, okay. I know that Denise ran it. So I saw what he gets. I think he got 59% or something. And he was doing it kind of next to me, so it took seconds. And in fact, it's going to be good to run on this, because you'll also see some interesting things if you look at your examples. What examples are generated? So you'll see, for example, that many of them are empty. You have to think about it. Yes. So probably there's some bugs.
Okay. Thanks so much.
Sure. Hi.
Uh,
Okay, good question. Where do you get the $100? I don't know about it. Oh, I didn't know that. So, who told you that? Okay, I'll ask him. I have no idea. I didn't think about it. But if
we can't, if we don't have GPU-based, the things we can approach for the final project.
yeah, that's true. So, I don't know if there are no GPUs that the engineering school.
Well, I have access
Provides?
to another pay grid, right? But my
Okay.
partner.
No, but
doesn't, so-
students, just for students, there's no. What are the competing resources that students have? Nothing?
From what I know, nothing.
Okay, I'll check. That's a very good question. So I'll check and say something about it.
Okay, thanks a lot.
Sure.
I have a question about the product and why it's equal to 2 to the power of, say, c. I don't understand the intuition behind why that measures the dot product because between two vectors. I think maybe because my linear algebra.
So here is what you do. I gave two examples. The one that I showed here and the one that I just write it down explicitly. I'm sure you'll be convinced.
I've done that and I counted and it's the same. So I know it's 2.
Oh, so you agree that the number is correct,
Yes,
but you
I
don't
just
know why.
Don't know why.
So here is how you think about it. You take the vectors, the t vectors. Do you understand the t vectors?
Yes, there are vectors in the t dimension.
Right. So in the case of dimension 3, which is my first example, you'll have 27 dimensions.
Okay.
You can write it down.
Okay.
Write the x and write the z, one above the other. What is the dot product? The dot product is the sum of the number of terms that align to 1 in both of them. Right?
Yeah, that's what we're doing when we count that.
That's a dot product.
That's a dot product?
Yeah, dot product is you take a vector of zeros and ones here and a vector of zeros and 1 here. What is the dot product? Is the number of coordinates where both of them are 1. That's a dot product.
I see. I thought dot product measures the distance between.
It's also true, but algebraically, you have two vectors that are Boolean. The dot product, so you see, you take x1 and z1 and multiply them. x2 and z2, multiply them.
Yeah.
If one of them is 0, this doesn't contribute to the sum. So really what you're doing in a dot product is you're counting the number of aligned ones.
I see. Okay. That makes a lot of sense now.
And therefore what you care about is how many of the t's will be 1 together.
I see. Okay. And that's the reason why you do it.
Yes.
I understand that, but I don't understand
The 2 to the power of thing. Oh,
why.
that's just me listing out the different examples.
I don't know when, like, when they both. Does that mean when they both won?
When they're both like this.
Or-
I think you list down the 27.
Yeah, I think that's what you should do. I mean, write down explicitly the example, it will convince you.
Thank
Okay.
you.
Sure.
Thank you.
Oh, excellent. So you have to announce and maybe also.
This week or next week, because I guess maybe
Oh,
we should
it's
announce
today.
it in class.
Okay,
Yeah, I got the email while just before the class.
okay, so maybe it's too late for today. Okay, so we'll do it next week. And so don't announce on Piazza now, because it will confuse people. Just after Wednesday.
Yeah.